Hello everyone, my name is Gary O'Mealy, and in this video we are going to discuss membrane transport. So the plasma membrane in a previous video we established is primarily made of phospholipids, proteins, cholesterol, and some carbohydrate chains that exist on the extracellular side. We haven't really talked a whole lot about the function of the membrane. The plasma membrane is commonly said to be semi-permeable, meaning that certain solutes can pass freely through the membrane from one side to another, while the movement of others is going to be highly restricted. Solutes that can cross the membrane do so by moving between the gaps in between adjacent phospholipids. So the idea here is that this red solute needs to be able to squeeze through the gaps in between neighboring phospholipids. But the thing we need to consider is that any particle that is going to try to do this is going to have to spend at least a little bit of time interacting with the hydrophobic tails in the hydrophobic core. Keeping in mind what we've talked about before about hydrophilic and hydrophobic substances, the hydrophobic tails in the middle are going to repel any hydrophilic substances. So for that reason, we can establish some rules that are going to dictate the ability of molecules to move through the membrane. Any given molecule or any given solute may have difficulty or may outright fail in getting through the membrane for three different reasons. Number one, the solute is too large. Very large molecules like macromolecules, proteins, nucleic acids, and things of that nature are usually going to be way too big to squeeze in between the little gaps in between neighboring phospholipids. So that's pretty simple to understand. The second idea is that the solute is too polar, meaning that it carries partial electrical charges, and this is going to usually consist of polar molecules that are hydrophilic and are not going to interact well with the hydrophobic tails that are in the middle of the hydrophobic core. A good example of this is glucose. Glucose, as we've established, carries a lot of polar hydroxyl functional groups, and these are not going to interact well with the hydrophobic tails. So even though glucose may be small enough to squeeze in between the phospholipids, it will be immediately repelled once it tries to enter into the hydrophobic core. So glucose will not be able to do this. And then finally, the solute is electrically charged, meaning that it is either a cation or an anion. This one is very easy to understand. Ions are going to be totally prevented from passing directly through the membrane because having a full electrical charge, like sodium here, is just a more extreme case of having partial electrical charges like we see in polar molecules. If polar molecules are going to be prevented from passing through because they carry partial charges, then ions are definitely going to be prevented from moving through because they carry full electrical charges. There is absolutely no way that a fully electrically charged solute will be able to pass through the membrane, whereas when it comes to polarity, there's scales to that, and there's such a thing as a molecule that is polar, but not so polar that it can't pass through. But in this case, it is extremely black and white. Fully electrically charged substances will not pass through. So therefore, we can design an ideal solute that will pass through the membrane most readily. The ideal solute will be very small, keeping in mind that atoms are smaller than molecules and molecules are smaller than macromolecules. Number two, it will be as nonpolar as it possibly can be. And number three, it should be electrically neutral. Again, a molecule may fail to pass through the membrane if it does not conform to any of these three terms. So let's look at a couple of examples of this. Let's start with oxygen gas. Oxygen is a dimolecular gas, meaning that a diatomic gas, meaning it consists of two oxygen atoms bound together. On the basis of size, it is extremely small, with a molecular weight of only 32 grams per mole. It is nonpolar, the two oxygen atoms are sharing their electrons equally, and it is electrically neutral. This is exactly the kind of molecule that can and does pass through the membrane freely. Similarly, carbon dioxide is small, 44 grams per mole, nonpolar. Those carbon-oxygen bonds are polar, but because they're oriented linearly, the dipoles cancel each other out. So on the whole, carbon dioxide is a nonpolar molecule. And finally, it is electrically neutral. So carbon dioxide, just as the case was with oxygen gas, can pass through membranes freely. If we consider physiological ions that we find in a variety of different bodily fluids, things like sodium and chloride and hydrogen and potassium, calcium and iodide, these all pass the size test because they are very small. In the case of hydrogen, that's about as small as anything is ever going to be at a atomic weight of 1 gram per mole. But the problem here is that these ions carry full electrical charges. So even though these ions are very small, they are much too electrically charged to ever pass through the membrane directly. We saw glucose before. Glucose is a little bit of a larger molecule with a molecular weight of 180 grams per mole. That's on the big side, but it's not so big that glucose wouldn't be able to pass through the membrane just based on its size alone. But the problem is that glucose is highly, highly polar. So the size already might have been a little bit of an issue, but the polarity makes it a non-starter. Glucose will not pass through the membrane all by itself. But in the case of ions and polar substances like glucose, you have to remember for now we are just talking about moving molecules directly through the membrane. Just because a solute cannot move directly through the membrane, that doesn't mean that it's never, ever, ever going to move through the membrane at all. What it will mean is that polar substances like glucose or ions, if they are going to move through the membrane, they just can't do it directly. They're going to need some kind of assistance to get through, and we will talk about that kind of assistance in the next video. Okay, so that's going to pretty much do it for this video. Here is a list of vocabulary terms you probably ought to be aware of, and for checking your understanding. Number 1, what is the major force that repels solutes away from the membrane? Number 2, which 3 molecular qualities determine the ability to move through the membrane and how? And finally, what are some examples of physiological solutes that might need to cross the membrane for a variety of different reasons? Okay, that's going to do it for this video. If you have a question, go ahead and drop it in the comments section, and I will see you for our next video in which we will start to talk about specific types of membrane transport. So long, and see you next time.